Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into a profound thought experiment. What would happen if 3IATLAS, our ancient cosmic visitor from another star system, had arrived on a collision course with Earth rather than passing safely through the outer solar system? If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In this alternate timeline, the first hints of catastrophe emerge not through dramatic announcements, but in the quiet accumulation of orbital calculations that reveal disturbing trajectory convergences. Astronomers tracking 3IATLAS through its approach to the inner solar system notice subtle deviations in predicted positions that, when extended forward through gravitational modeling, reveal impact probabilities that steadily increase from statistical noise toward mathematical certainty. The same non-gravitational forces that created measurement challenges during the comet's actual passage now conspire to bend its trajectory toward a rendezvous with Earth's orbital path. Computer simulations running continuously in observatories around the globe refine impact predictions with each new astrometric measurement, narrowing uncertainty ellipses that initially encompassed vast regions of space down to specific impact zones on Earth's surface. The mathematical precision of celestial mechanics transforms from academic exercise to existential calculation as orbital integrators compute approach velocities, impact angles, and energy release estimates that dwarf any natural disaster in recorded human history. Deep Space Network radar installations begin dedicated tracking campaigns that confirm the approaching object's dimensions and composition through reflected radio waves, revealing a nucleus approximately 2 kilometers in diameter with mass estimates approaching 10 billion tons, traveling at relative velocities exceeding 26 kilometers per second. These measurements establish the fundamental parameters that will determine impact consequences, kinetic energy calculations that approach the explosive yield of millions of nuclear weapons concentrated into a single geological instant. Planetary defense protocols activate coordination between international space agencies, military organizations, and scientific institutions as the recognition spreads that 3IATLAS represents the first confirmed interstellar impactor threatening Earth in human history. The exotic composition and alien formation history that made this cosmic wanderer scientifically fascinating now transforms it into an unprecedented hazard that carries within its ancient nucleus materials and energy signatures unknown to terrestrial impact modeling. The discovery that impact trajectory intersects densely populated continental regions rather than oceanic areas amplifies catastrophe predictions. As computer models reveal that land impacts generate more severe atmospheric disturbances and ejector distribution patterns compared to oceanic collisions, geographic impact coordinates calculated through orbital mechanics become the focus of evacuation planning and infrastructure protection strategies operating under time constraints measured in weeks rather than the years typically available for natural disaster preparation. Only took gravitational mechanics a few months to transform 3IATLAS from scientific curiosity into existential threat, demonstrating how cosmic wanderers could theoretically transition from observational targets to impact hazards through orbital evolution processes that operate according to the same physical laws governing planetary motion. The patient mathematics of celestial mechanics reveals scenarios where cosmic encounters that begin as safe passages could evolve into direct collisions through accumulation of small trajectory modifications. International coordination efforts reveal the inadequacy of existing planetary defense infrastructure for responding to interstellar impactors, whose approach velocities and exotic compositions exceed the design parameters of deflection systems developed for conventional asteroid and comet threats. The enhanced approach speed means that detection to impact timescales shrink dramatically compared to solar system objects, while alien material properties create uncertainties in explosive deflection, effectiveness, and nuclear device coupling efficiency. Media coverage begins transitioning from scientific wonder to public safety information, as impact probability estimates exceed statistical significance thresholds, and emergency management agencies worldwide initiate preliminary evacuation planning for impact zones and surrounding regions likely to experience severe secondary effects. The same isotopic signatures and organic compounds that captivated astrobiologists now become environmental contamination concerns requiring hazmat protocols and biological containment strategies. Atmospheric entry modelling reveals that 3IATLAS would retain substantial mass through its passage to Earth's surface, with ablation calculations indicating that perhaps 70% of the original nucleus would survive atmospheric heating to create ground impact rather than airburst explosion. This survival fraction means that impact energy calculations must account for nearly the full kinetic energy content, rather than the reduced values typical of objects that fragment completely during atmospheric passage. Impact timing predictions converge towards specific calendar dates and geographic coordinates, as continued observations reduce orbital uncertainties and establish precise approach geometry, transforming abstract mathematical probabilities into concrete predictions of when and where 10 billion tons of interstellar material would strike Earth's surface at cosmic velocities. The astronomical precision of these calculations provides both clarity and helplessness, perfect knowledge of approaching catastrophe with limited capability for prevention. Economic modelling of impact consequences reveals disruption scenarios that exceed conventional disaster planning frameworks, with global supply chain interruptions, agricultural disruptions, and infrastructure damage that could persist for decades beyond the initial impact event. The recognition that interstellar impacts carry consequences that transcend local or regional effects highlights fundamental vulnerabilities in civilization's dependence on stable environmental conditions and functional technological infrastructure. Scientific research priorities shift from compositional analysis to impact mitigation studies as research institutions worldwide redirect resources toward understanding deflection possibilities, atmospheric shielding effects, and post-impact recovery strategies. The same instruments that decoded 3IATLAS's alien chemistry now focus on practical questions of survival and planetary protection against cosmic threats that arrive without warning from interstellar space. Emergency preparedness agencies worldwide begin developing response protocols for scenarios that exceed all previous disaster planning experience, creating evacuation procedures, resource stockpiling strategies, and communication plans for managing populations during events that could disrupt global civilization for extended periods. These preparations operate according to impact timeline constraints that compress normal disaster response planning from years of preparation into weeks of frantic organization. The psychological impact of confirmed collision course predictions begins affecting global populations As the recognition spreads that Earth faces an unprecedented natural disaster whose consequences could reshape planetary civilization and environmental conditions in ways that remain largely unpredictable, based on limited experience with cosmic impacts of similar magnitude. The intersection of scientific precision with existential uncertainty creates societal responses that range from resignation to determination across different cultural and geographical contexts. The atmospheric entry of 3IATLAS would begin approximately 100 kilometers above Earth's surface as the cosmic wanderer encounters the first tenuous molecules of the thermosphere, where initial friction creates a faint glow that marks the beginning of the most spectacular and terrifying light show in human history. Traveling at 26 kilometers per second, nearly 100 times faster than typical meteorites, the interstellar visitor would compress atmospheric gases ahead of its nucleus into a superheated plasma sheath that radiates energy across the electromagnetic spectrum, from radio waves through visible light to high-energy X-rays. The hypersonic shockwave generated by the object's passage would create a luminous tunnel through Earth's atmosphere, where compressed air reaches temperatures exceeding 10,000 degrees Celsius, hot enough to dissociate molecular bonds and ionize atmospheric gases into glowing plasma that traces the incoming trajectory like a cosmic lightning bolt stretching across hundreds of kilometers of sky. This plasma trail would appear brighter than the sun to observers within thousands of kilometers, creating temporary daylight conditions even during nighttime impact scenarios. Atmospheric heating begins ablating material from the nucleus surface within seconds of initial atmospheric contact, stripping away layers of exotic ices and organic compounds that vaporize into expanding clouds of alien chemistry mixed with superheated terrestrial atmosphere. Mass spectrometric analysis of this ablation plume would reveal the cosmic visitor's interstellar composition through spectroscopic emissions that paint the sky with wavelengths corresponding to elements forged in distant stellar furnaces and molecular compounds unknown to Earth's atmospheric chemistry. The extraordinary entry velocity means that atmospheric braking forces remain insufficient to significantly decelerate the massive nucleus during its brief passage through Earth's atmospheric layers, with flight time from initial contact to surface impact measuring only seconds rather than the minutes typical of solar system objects. Computer simulations reveal that 3IATLAS would lose perhaps 30% of its mass to atmospheric ablation, while retaining enough structural integrity to deliver approximately 7 billion tons of interstellar material to Earth's surface at velocities still exceeding 20 kilometers per second. Electromagnetic effects from the ionized plasma trail would create radio blackouts across entire continental regions as the conductive plasma channel absorbs and scatters radio frequency transmissions, disrupting communication systems and navigation satellites throughout the electromagnetic storm created by atmospheric passage. These ionospheric disturbances would persist for hours after impact, as the ionized atmosphere gradually recombines and returns to normal electrical properties. Only took atmospheric friction a few seconds to convert portions of 3IATLAS's kinetic energy into electromagnetic radiation and thermal heating that would be visible from space as a brilliant streak crossing Earth's night side like a second sunrise racing across continents at hypersonic velocity. Astronauts aboard the International Space Station would witness the entire atmospheric entry sequence as a blazing trail that outshines all terrestrial lighting and creates auroral displays through magnetic field interactions with the ionized entry corridor. Acoustic effects from the hypersonic shockwave would generate sonic booms with amplitudes far exceeding those produced by supersonic aircraft. creating atmospheric pressure waves that could shatter windows and damage structures across regions measuring hundreds of kilometers in diameter. The acoustic energy released during atmospheric passage would exceed the sound levels produced by volcanic eruptions and create infrasonic waves that propagate around the globe multiple times as Earth's atmosphere rings like a struck bell. Atmospheric chemistry modifications would occur as the ablating nucleus introduces exotic compounds and isotopic signatures into Earth's atmospheric composition, creating chemical traces that could be detected in atmospheric samples collected worldwide for decades after impact. These alien chemical signatures would include deuterium-enriched water vapor, isotopically anomalous carbon dioxide, and organic molecules with chirality patterns that differ from terrestrial biochemistry. The plasma trail formation would create temporary modifications to Earth's magnetic field as the conductive ionized gas interacts with the planetary magnetosphere, generating magnetic disturbances that could affect satellite operations and create auroral displays at latitudes far from typical aurora zones. These magnetospheric interactions would propagate electromagnetic effects throughout Earth's space environment and create temporary modifications to radiation belt structure. Thermal radiation from the superheated plasma would deposit energy throughout the atmospheric column along the entry trajectory, creating temporary heating effects that could influence local weather patterns and atmospheric circulation in ways that persist for days or weeks after passage. The thermal energy release would exceed that of major volcanic eruptions and create atmospheric temperature anomalies detectable by meteorological monitoring systems worldwide. Fragmentation possibilities during atmospheric passage could create multiple impact sites if structural failure breaks the nucleus into large fragments that separate during entry, spreading impact effects across wider geographic regions while reducing individual crater sizes. Computer modeling reveals that appropriate failure modes could create impact patterns ranging from single massive craters to distributed impact fields spanning hundreds of kilometers. Chemical reactions between ablated nucleus material and atmospheric gases would create exotic chemical compounds that exist only under the extreme temperature and pressure conditions present during hypersonic atmospheric entry, producing molecular species that might never form under normal terrestrial conditions. These reaction products would add additional complexity to atmospheric contamination patterns and create unique chemical signatures in environmental samples collected after impact. Optical effects from atmospheric scattering of plasma radiation would create spectacular visual phenomena, including unusual cloud formations, atmospheric distortions, and lighting effects that would be visible across entire hemispheres as scattered light from the plasma trail illuminates atmospheric particles and moisture. These optical displays would provide the last visual warning before impact for populations within the affected regions. The atmospheric entry corridor would experience temporary atmospheric evacuation as shockwave effects displace atmospheric gases and create partial vacuum conditions behind the passing object, generating complex fluid dynamics where atmospheric backflow could create secondary shock waves and turbulence effects that persist long after the object's passage to the surface. Radiation effects from the high-energy plasma would create temporary increases in cosmic ray exposure for aircraft and high-altitude installations as electromagnetic radiation and particle acceleration within the plasma column generate radiation levels that could affect electronic systems and create hazardous exposure conditions for personnel in affected regions. Meteorological monitoring stations worldwide would detect atmospheric pressure waves, temperature anomalies, and electromagnetic disturbances that propagate outward from the entry corridor at the speed of sound and electromagnetic wave propagation, creating global atmospheric signatures that would be recorded by seismographic, magnetometric, and atmospheric monitoring instruments throughout the planet's surface and orbital monitoring networks. The kinetic energy calculations for 3IATLAS's hypothetical Earth impact reveal numbers that stretch beyond ordinary comprehension. Approximately 7 billion tons of interstellar material traveling at 26 kilometers per second would release energy equivalent to 50 million megatons of TNT, surpassing the explosive yield of humanity's entire nuclear arsenal, detonated simultaneously in a single geological instant. This energy release exceeds the largest volcanic eruptions in Earth's recorded history and approaches the magnitude of impacts that created global extinction events preserved in the geological record as mass extinction boundaries, marking the deaths of entire biological eras. Computer simulations of energy transfer during impact reveal that the incoming kinetic energy would convert instantaneously to thermal, seismic, and mechanical energy through collision processes that operate over timescales measured in seconds, while releasing energy at rates exceeding the total power consumption of human civilization by factors of millions. The impact energy density would create temperature and pressure conditions that approach those found in stellar interiors, generating plasma states where atomic nuclei separate from electrons and matter exists as free charged particles rather than conventional atomic structures. Thermodynamic modeling indicates that impact energy release would vaporize both the incoming nucleus and substantial quantities of target rock, creating expanding clouds of superheated vapor with temperatures exceeding 10,000 degrees Celsius and pressures that dwarf those found in deep ocean trenches. This vapor expansion would operate through explosive mechanisms analogous to nuclear weapon detonations, yet sustained over longer timescales and involving mass quantities that exceed nuclear explosion scales by factors of millions. The energy release rate during impact would generate electromagnetic effects comparable to solar flare activity, as accelerating charged particles create magnetic field disturbances and radio frequency emissions that propagate throughout Earth's magnetosphere and into interplanetary space. These electromagnetic signatures would be detectable by radio astronomy facilities throughout the solar system and create distinctive signals that could theoretically alert extraterrestrial observers to major geological events occurring on Earth. Material property analysis of 3IATLAS's exotic composition suggests that impact energy release could differ significantly from conventional rocky or icy impactors due to unusual thermal conductivity, structural strength, and chemical bonding characteristics that influence energy transfer efficiency during collision events. Laboratory studies of analog materials indicate that certain exotic compositions could create enhanced energy, coupling that amplifies impact effects beyond predictions based on conventional solar system materials. Only took the laws of physics a few microseconds to convert millions of years of accumulated kinetic energy into thermal and mechanical energy release that would reshape local geology and atmospheric chemistry in ways that persist for millions of years in Earth's environmental and geological records. The instantaneous nature of energy conversion contrasts dramatically with the gradual accumulation of kinetic energy during the comet's cosmic wandering through interstellar space over geological timescales. Comparative analysis with historical impact events preserved in Earth's geological record reveals that 3IATLAS would deliver energy comparable to the Chicxulub impactor that contributed to dinosaur extinction 65 million years ago, placing this hypothetical impact among the most energetic geological events in Earth's history, and potentially triggering environmental changes with global consequences for biological systems and atmospheric chemistry. Energy partition calculations indicate that approximately 10% of impact kinetic energy would convert to seismic wave propagation through Earth's crust and mantle, creating earthquake effects that exceed the most powerful seismic events in recorded history, while generating vibrations that propagate completely around the globe and create measurable ground motion on the opposite side of the planet from impact location. Atmospheric shockwave generation would consume additional portions of impact energy through compression heating and acoustic wave propagation that create atmospheric pressure disturbances capable of causing structural damage across continental regions. With shock wave amplitudes that could flatten forests and destroy buildings across areas measuring thousands of square kilometers around the impact site, the discovery that interstellar impact velocities exceed typical solar system collision speeds by factors of 2 to 3 means that energy scaling relationships derived from conventional impact studies underestimate the effects of interstellar impactors, requiring development of new theoretical frameworks for predicting impact consequences at velocity regimes that remain largely unexplored through terrestrial impact experiments and computer modeling studies. Nuclear reaction possibilities within impact-generated plasma could create additional energy release through fusion processes triggered by extreme temperature and pressure conditions, potentially supplementing kinetic energy release with nuclear energy generation that could amplify total energy output beyond pure kinetic energy calculations. These nuclear enhancement effects remain theoretical, but could significantly increase impact energy estimates under appropriate physical conditions. Energy density comparisons reveal that 3IATLAS impact would concentrate more energy per unit volume than any natural terrestrial process except nuclear reactions, creating local physical conditions that exceed those found in volcanic eruptions, earthquake fault zones, and explosive geological events by margins that challenge theoretical understanding of matter behavior under extreme energy density conditions. Temporal energy release profiles indicate that impact energy deposition would occur over timescales ranging from microseconds for initial collision effects to minutes for atmospheric shockwave propagation and hours for global seismic wave transmission, creating complex energy transfer cascades where initial impact energy triggers secondary effects that redistribute energy throughout Earth's environmental systems over extended time periods. Conservation of energy principles require that the enormous kinetic energy content of 3IATLAS be transformed into other energy forms during impact, with thermal energy generation sufficient to vaporize rock volumes, measuring cubic kilometers, while seismic energy release creates permanent modifications to crustal structure, and acoustic energy generation produces atmospheric disturbances that propagate around the globe multiple times. Experimental validation of energy release calculations requires extrapolation from laboratory impact studies, conducted at much smaller scales and lower velocities, introducing uncertainties in energy scaling relationships that could affect impact consequence predictions by substantial factors. These scaling uncertainties highlight fundamental limitations in current understanding of energy transfer processes operating under extreme impact conditions. The implications of such enormous energy release extend beyond immediate impact effects to encompass global environmental modifications that could influence climate systems, atmospheric chemistry, and biological processes for decades or centuries after impact, demonstrating that interstellar impact events represent geological phenomena with consequences that transcend local destruction to encompass planetary-scale environmental change. Future impact energy calculations for interstellar objects would benefit from enhanced theoretical understanding of energy transfer processes operating under extreme velocity and pressure conditions, requiring development of new computational models and experimental techniques capable of investigating physical processes that operate under parameters far exceeding current laboratory capabilities and terrestrial experience with natural impact events. The moment of impact between 3I-ATLAS and Earth's surface would initiate a crater formation process of staggering proportions, excavating a circular depression measuring approximately 30 kilometers in diameter and 10 kilometers in depth, a permanent geological scar that would rank among the largest impact structures preserved in Earth's cratering record. The excavation process would operate through shockwave mechanics that instantaneously accelerate target rock to velocities exceeding several kilometers per second, launching millions of tons of pulverized material into ballistic trajectories that distribute excavated debris across continental regions. Computer simulations of crater formation reveal that the impact would proceed through distinct phases, beginning with contact compression, where the incoming nucleus transfers momentum to target rock through shockwave generation, followed by excavation flow, where compressed rock rebounds and flows outward from the impact point, and finally gravitational collapse, where the temporary crater cavity partially fills through slumping of unstable crater walls. These crater formation stages would complete within minutes of initial impact, yet create geological modifications that persist for millions of years. The central uplift structure, typical of large impact craters, would create a mountainous peak rising several kilometers above the surrounding crater floor as deep crustal rocks rebound from shock compression and flow upward through mechanisms analogous to droplet splash formations scaled up to geological dimensions. This central peak would expose crustal rocks that normally remain buried kilometers below the surface, creating natural laboratories where deep earth materials become accessible for scientific study and mineral extraction. Shock metamorphism within the impact zone would transform ordinary sedimentary and igneous rocks into high-pressure mineral phases that exist only under extreme pressure conditions, comparable to those found in Earth's deep mantle, creating distinctive mineralogical signatures that preserve evidence of impact processes in crystalline structures that remain stable for geological timescales. These shock-produced minerals would include diamond, stishovite, and other high-pressure phases that require pressures exceeding those achievable through normal geological processes. The crater rim structure would consist of uplifted and overturned rock layers that create circular mountain ranges surrounding the central depression, with peak heights that could exceed 2 kilometers above the pre-impact surface elevation. These rim mountains would expose geological cross-sections that reveal millions of years of Earth's crustal history, while creating distinctive topographic features that influence regional drainage patterns, weather systems, and ecological development for millions of years after formation. Only took shockwave propagation a few seconds to excavate volumes of rock that would require millions of years to remove through normal erosional processes, demonstrating the extraordinary efficiency of impact excavation compared to gradual geological processes that shape planetary surfaces over extended timescales. The rapid excavation creates instantaneous geological changes that would normally require millions of years of tectonic and erosional activity to achieve through conventional geological mechanisms. Ejecta blanket deposition would cover the surrounding landscape with layers of shocked and melted rock debris that extends hundreds of kilometers from the crater rim, creating distinctive geological formations where mixed crustal materials form chaotic breccia deposits that preserve fragments of the original target rock, along with traces of the impacting nucleus. These ejecta deposits would create new geological formations that alter local topography and soil chemistry across regions measuring thousands of square kilometers. Impact melt generation would produce vast quantities of molten rock that pools within the crater cavity and creates extensive lava lake systems that could remain molten for thousands of years after impact, generating distinctive igneous rock formations through cooling and crystallization processes that operate under conditions unlike normal volcanic activity. The chemical composition of impact melts would preserve mixing signatures between terrestrial target rock and alien nucleus materials. Fractional melting effects would create chemical differentiation within impact melt sheets, where different mineral components separate according to density and melting point differences, generating layered igneous rock formations with compositional gradients that record the thermal history of impact energy deposition and subsequent cooling processes. These melt differentiation patterns would provide detailed records of impact energy distribution and thermal evolution. The discovery that interstellar nucleus materials would become intimately mixed with terrestrial rock during crater formation means that alien chemical signatures would become permanently incorporated into Earth's geological record, creating distinctive isotopic and compositional anomalies that could be detected in crater rocks for billions of years after impact. These alien signatures would include exotic isotope ratios and trace element patterns that differ systematically from normal terrestrial geological materials. Structural deformation extending beyond the visible crater would create zones of fractured and brecciated rock that extend several crater diameters from the impact site, generating permanent modifications to crustal architecture that influence groundwater flow, seismic wave propagation, and mineral deposit formation across much larger regions than the visible crater structure. These structural modifications would create long-term geological effects that persist throughout subsequent geological evolution. Crater preservation potential depends on subsequent geological processes including erosion, sedimentation, and tectonic activity that could either preserve or destroy crater structures over geological timescales, with preservation probability depending on local geological conditions and climatic factors that determine erosion rates and sedimentation patterns. Large craters in stable continental regions could potentially remain recognizable for billions of years. Hydrogeological effects from crater formation would create new drainage patterns and groundwater flow systems as crater topography and fractured bedrock alter surface water and subsurface water movement across regional scales, potentially creating new lake systems, wetlands, and aquifer configurations that influence regional hydrology and ecological development for millions of years after impact. Comparative analysis with existing terrestrial impact structures reveals that 3I-ATLAS crater would exceed all but the largest preserved impact features on Earth, ranking among geological structures like Vredefort and Sudbury that represent ancient impact events whose crater formation processes shaped regional geology and influenced subsequent geological evolution through modification of crustal structure and topographic relief. Economic implications of crater formation include both destructive effects from excavation of existing infrastructure and resources within the impact region, and potential beneficial effect from exposure of deep crustal rocks that could contain valuable mineral deposits normally inaccessible through surface mining operations. These economic effects would operate over timescales spanning immediate destruction through long-term resource development opportunities. The implications of creating such a massive crater extend beyond geological modification to encompass permanent alterations to regional geography, hydrology, and ecology that would influence human settlement patterns, agricultural development, and natural resource distribution for thousands of years after impact, demonstrating that crater formation represents not just geological change but fundamental reshaping of regional environmental conditions and human land use possibilities. The seismic energy release from 3IATLAS's impact would generate earthquake waves of unprecedented magnitude that propagate outward through Earth's crust and mantle at velocities approaching 8 kilometers per second, creating the most powerful seismic event in recorded human history, with magnitude estimates exceeding 11 on the Richter scale, an earthquake so severe that it transcends conventional seismic classification systems developed for tectonic earthquake phenomena. These shock waves would carry sufficient energy to trigger secondary earthquakes along existing fault systems worldwide, as the impact-generated seismic pulse destabilizes critically stressed geological structures across multiple continents. Primary seismic waves radiating outward from the impact site would create ground accelerations that exceed the tolerance limits of engineered structures across regions measuring thousands of kilometers in diameter, with peak ground velocities that could approach several meters per second and generate vertical accelerations sufficient to launch objects and people temporarily airborne. The severity of ground motion would exceed design specifications for earthquake-resistant construction by factors that render even the most robust engineering standards inadequate for survival. Surface wave propagation across continental regions would create rolling ground motions that persist for hours after initial impact, as different seismic wave types arrive at distant locations, with timing delays that depend on wave velocity and propagation path geometry through Earth's interior. Rayleigh waves travelling along Earth's surface would create undulating ground motions that resemble ocean swells, translated to solid rock, with wavelengths measuring kilometers and amplitudes exceeding several meters. The discovery that seismic waves from major impacts can propagate completely around the globe means that 3IATLAS would generate measurable ground motion on the opposite side of Earth from the impact site, creating antipodal focusing effects where seismic energy converges after travelling through Earth's core, and could potentially trigger volcanic activity or fault rupture in regions geographically distant from the primary impact zone. Seismic wave interaction with Earth's internal structure would reveal detailed information about planetary interior properties as impact-generated waves probe density variations, phase boundaries, and compositional heterogeneities throughout the mantle and core, with unprecedented resolution and energy levels. These seismic measurements would provide scientific data about Earth's deep interior that could advance geophysical understanding by decades through a single catastrophic event. Only took seismic wave propagation a few minutes to carry impact energy to continental distances and several hours to generate measurable effects at global scales, demonstrating how instantaneous geological events can create mechanical disturbances that influence planetary-scale geophysical processes and trigger secondary effects in regions far removed from primary impact locations. Fault activation along existing tectonic boundaries would create cascading earthquake sequences as impact-generated stress waves trigger rupture along fault systems that had accumulated tectonic stress over geological timescales, potentially generating major earthquakes along the San Andreas Fault, Japan Trench, and other seismically active regions worldwide. These triggered earthquakes could produce additional casualties and infrastructure damage that exceeds direct impact effects in certain geographical regions. Lovewave generation would create horizontal ground shaking that propagates through continental crustal structures with particular efficiency, generating side-to-side ground motion that proves especially destructive to tall buildings and infrastructure systems designed primarily to resist vertical loading rather than lateral displacement. These horizontal accelerations could cause widespread structural collapse across urban areas located hundreds of kilometers from the impact site, The mystery of seismic wave amplification in sedimentary basins means that cities built on unconsolidated sediments would experience enhanced ground shaking as seismic waves become trapped and amplified within soft geological layers that act like resonant cavities for earthquake energy. Metropolitan areas situated on river deltas, coastal plains, and sedimentary valleys would experience disproportionately severe damage compared to cities built on solid bedrock foundations. Tsunami generation becomes possible if impact occurs in oceanic regions where sudden seafloor displacement creates massive water displacement that propagates across ocean basins as tsunami waves, with wavelengths measuring hundreds of kilometers and wave heights that could exceed those generated by the most powerful underwater earthquakes. These impact-generated tsunamis would carry enormous energy content and create coastal devastation across entire ocean basins. Liquefaction effects in saturated sediments would transform solid ground into fluid-like suspensions as seismic shaking disrupts soil structure and causes groundwater to flow upward through loosened sediment layers, creating quicksand-like conditions across extensive regions where infrastructure and buildings sink or topple due to sudden loss of foundation support. Induced seismicity in regions with enhanced geothermal activity could trigger volcanic eruptions as seismic waves disrupt magma chamber stability and modify subsurface pressure conditions that control volcanic activity, potentially creating simultaneous volcanic and seismic hazards that compound disaster response challenges across multiple affected regions. Seismographic station networks worldwide would record impact-generated seismic signals with unprecedented clarity and amplitude, providing detailed datasets for studying seismic wave propagation through Earth's interior, while simultaneously documenting the most catastrophic geological event in recorded human history. These seismic records would advance scientific understanding of both impact processes and Earth's internal structure. Infrastructure vulnerability analysis reveals that transportation networks, communication systems, and utility infrastructure would experience widespread failure across continental regions as seismic damage severes critical connections and creates cascading system failures that persist long after seismic shaking subsides. Recovery efforts would face enormous challenges in re-establishing basic services across regions affected by unprecedented ground motion. Building response modeling indicates that even earthquake-resistant structures would experience failure modes not encountered in conventional seismic design scenarios, as impact-generated ground motions exceed design parameters and create loading conditions that surpass engineered safety margins by substantial factors. Modern seismic building codes provide insufficient protection against impact-generated earthquake magnitudes. The persistence of aftershock activity could continue for months or years after initial impact as disturbed crustal stress patterns gradually readjust through continued seismic activity, creating ongoing earthquake hazards that complicate reconstruction efforts and maintain elevated seismic risk levels across affected regions long after the primary impact event. Paleoseismic evidence preserved in geological formations would record the 3IATLAS impact earthquake in stratigraphic sequences that remain detectable for millions of years, creating permanent geological records of catastrophic seismic events that could be recognized by future geological surveys as evidence of major impact events in Earth's geological history. The catastrophic excavation of 3IATLAS's impact crater would launch millions of tons of vaporized rock, molten debris, and alien materials into ballistic trajectories that distribute impact ejecta across hemispheric distances, creating a global blanket of mixed terrestrial and interstellar materials that settles onto Earth's surface like deadly snow falling from space. Computer simulations reveal that the most energetic ejecta fragments would achieve escape velocity and temporarily enter orbit around Earth before falling back to create secondary impact craters across continents, while intermediate velocity debris follows parabolic trajectories that deliver superheated rock fragments to locations thousands of kilometers from the primary impact site. The ejecta curtain rising from the impact crater would create a spectacular and terrifying dome of incandescent material expanding outward at velocities measuring several kilometers per second, forming a hemispherical wall of molten rock and vaporized debris that glows with temperatures exceeding those found in steel furnaces. This expanding curtain of destruction would be visible from space as a growing circle of luminous material that temporarily outshines city lights and creates auroral displays as charged particles interact with Earth's magnetic field. Ballistic range calculations indicate that the largest coherent ejecta blocks, rocky fragments measuring meters to tens of meters in diameter, would travel distances exceeding 1,000 kilometers before impacting Earth's surface with sufficient kinetic energy to create secondary craters and trigger local fires through impact heating. These secondary impacts would pepper continental regions with crater fields that resemble lunar highland terrain, creating permanent modifications to local topography across vast geographical areas. The temporal sequence of ejecta arrival creates waves of destruction that arrive at different times depending on fragment size and launch velocity, with the fastest particles arriving minutes after impact, followed by progressively larger and slower debris over periods measuring hours to days. This extended bombardment means that affected regions experience repeated episodes of destruction as different ejecta size classes arrive according to their ballistic flight times. Atmospheric heating effects from ejecta re-entry would create spectacular fireball displays as returning debris burns through Earth's atmosphere at hypervelocity speeds, generating meteor shower phenomena with intensities that exceed natural meteor storms by factors of millions. The collective thermal radiation from thousands of simultaneous re-entry events would create infrared heating sufficient to ignite vegetation and structures across continental regions, triggering widespread fires that could consume entire ecosystems. Only took impact excavation a few seconds to launch debris on trajectories that would continue delivering destruction for hours or days as ballistic mechanics govern the return of impact materials to Earth's surface across global distances, demonstrating how instantaneous geological events can create extended periods of environmental hazard through the delayed arrival of impact-generated projectiles. Chemical composition analysis of ejecta blankets would reveal intimate mixing between terrestrial target rock and alien nucleus materials, creating distinctive geological formations where Earth rocks contain embedded fragments of interstellar materials with isotopic signatures and chemical compositions that differ dramatically from any natural terrestrial rock formation. These mixed formations would preserve evidence of interstellar contamination in geological deposits that persist for millions of years. Thermal effects from impact-heated ejecta would create significant fire hazards as molten rock fragments ignite vegetation, structures, and fuel deposits across regions measuring thousands of square kilometers around the impact site. The thermal radiation from glowing ejecta particles suspended in the atmosphere would create greenhouse effects that could raise local temperatures sufficiently to cause heat stroke and equipment failure across extensive geographical areas. Particle size distribution within ejecta clouds would span enormous ranges from microscopic dust grains that remain suspended in the atmosphere for months to boulder-sized fragments that create local cratering upon impact, generating complex sedimentation patterns where fine particles create uniform dust layers while larger fragments create localized destruction and contamination. These size-dependent effects mean that ejecta impacts would vary dramatically across different geographical regions. The discovery that impact angle and target geology significantly influence ejecta distribution patterns means that oblique impacts could create asymmetric ejecta blankets that preferentially affect specific geographical regions while sparing others, potentially creating uneven global distribution of impact effects that depend on the precise impact trajectory and geological characteristics of target materials at the impact site. Electromagnetic effects from electrically charged ejecta particles would create atmospheric electrical phenomena as triboelectric charging during high-velocity atmospheric passage generates static electricity that could produce lightning displays and electromagnetic pulse effects across regions affected by ejecta bombardment. These electrical effects could damage electronic systems and create additional fire hazards through electrical discharge phenomena. Ocean impact from ejecta fragments would create steam explosions and water displacement that generate tsunami waves while simultaneously introducing superheated rock into marine environments, creating complex interactions between thermal, mechanical, and chemical effects that could devastate marine ecosystems across oceanic regions. The rapid cooling of molten ejecta in seawater would create distinctive volcanic glass formations on ocean floors. Agricultural contamination from ejecta deposition would render vast agricultural regions unusable for crop production, as heavy metal contamination and chemical toxicity from alien materials create soil conditions that prove lethal to terrestrial plant life, potentially triggering global food shortages that persist for years or decades after impact, as contaminated soils require extensive remediation before agricultural restoration becomes possible. Construction material formation through impact processes would create new geological resources as shock metamorphism and thermal processing generate distinctive rock types with unique physical and chemical properties that could prove valuable for construction applications, providing long-term economic benefits that partially offset the enormous destruction caused by impact effects. Atmospheric suspension of fine ejecta particles would create persistent dust clouds that reduce solar radiation reaching Earth's surface, while simultaneously creating enhanced sunset and sunrise displays as suspended particles scatter sunlight in ways that generate spectacular optical phenomena. These atmospheric effects would influence global climate patterns and create distinctive optical signatures that persist for months after impact. Biological preservation within impact ejecta could theoretically allow terrestrial organisms to survive ballistic transport to distant locations if they become embedded within protective rock matrices during crater excavation, creating potential mechanisms for biological dispersal across continental distances through impact-generated transportation that operates over timescales much shorter than normal biological migration processes. Paleontological significance of ejecta blankets would preserve detailed records of Earth's biological and geological state at the moment of impact, creating time marker horizons in sedimentary sequences that could be recognized in future geological surveys as evidence of catastrophic impact events, while simultaneously preserving fossil assemblages that document pre-impact biological communities. The massive quantities of pulverized rock and vaporized debris launched into Earth's atmosphere by 3IATLAS's impact would create a global dust shroud that blocks solar radiation and plunges the planet into an extended period of artificial darkness, resembling nuclear winter scenarios, yet sustained over timescales that could persist for months or years, depending on particle size distributions and atmospheric circulation patterns. Computer climate models predict that atmospheric dust loading would reduce solar irradiance reaching Earth's surface by 60 to 90%, creating temperature drops that could exceed 10 degrees Celsius globally and trigger widespread crop failures across agricultural regions worldwide. Atmospheric particle physics reveals that impact-generated dust consists of mixed populations, ranging from microscopic clay-sized particles that remain suspended for years to larger silt-sized grains that settle within months, creating complex atmospheric opacity effects where different wavelengths of solar radiation experience varying degrees of attenuation depending on particle size distributions and altitude profiles of suspended debris. The finest particles would penetrate into the stratosphere where atmospheric circulation patterns distribute them globally within weeks of impact. Photosynthetic disruption across terrestrial and marine ecosystems would begin within days of atmospheric darkening as reduced solar radiation falls below the minimum energy requirements for plant metabolism, triggering widespread die-offs of primary producers that form the foundation of global food webs. The collapse of photosynthetic activity would cascade through ecological systems as herbivorous species lose food sources and carnivorous species experience subsequent population crashes, creating ecosystem-wide disruptions comparable to mass extinction events preserved in Earth's geological record. Temperature reduction effect would prove most severe in continental interior regions, where atmospheric dust combines with reduced solar heating to create winter-like conditions even during normal warm seasons, generating frost events and freezing temperatures that destroy temperature-sensitive vegetation and create agricultural disasters across temperate and tropical regions unaccustomed to sustained cold conditions. Coastal regions would experience moderated cooling effects due to oceanic thermal buffering, yet still suffer significant temperature reductions. The discovery that atmospheric dust particles provide nucleation sites for water droplet formation means that global precipitation patterns would change dramatically, as enhanced cloud formation creates increased rainfall and snowfall in some regions, while other areas experience reduced precipitation due to altered atmospheric circulation patterns driven by temperature gradients between dust-laden and cleaner atmospheric regions. Only took atmospheric circulation a few weeks to distribute impact dust around the globe and create planetary-scale climate modifications that would persist for months or years, as gravitational settling gradually removes suspended particles from the atmosphere, according to size-dependent fall velocities that determine atmospheric residence times for different particle populations. Infrared radiation absorption by suspended dust particles would create complex radiative effects, where atmospheric heating from absorbed solar and terrestrial radiation partially offsets surface cooling effects. Yet overall energy balance calculations indicate net cooling, as reduced solar transmission exceeds atmospheric heating effects. These radiative interactions would create atmospheric temperature profiles that differ significantly from normal atmospheric structure. Agricultural impact assessments reveal that global food production would decline catastrophically as crop failures affect temperate grain-producing regions that provide staple foods for billions of people, while tropical agricultural systems experience unprecedented cold stress that destroys heat-sensitive crops and disrupts growing seasons. Livestock populations would face feed shortages as grasslands and fodder crops fail under reduced solar radiation conditions. The mystery of atmospheric chemistry modifications arises as impact vaporized materials introduce exotic chemical species into Earth's atmosphere, potentially creating acid rain effects if sulfur-bearing minerals from the impact site generate atmospheric sulfuric acid that increases precipitation acidity and creates additional environmental stress for surviving biological systems already struggling with reduced solar radiation and temperature stress. oceanic cooling effects would develop more gradually than atmospheric temperature changes as the enormous thermal mass of seawater buffers temperature reductions. Yet sustained atmospheric cooling would eventually reduce sea surface temperatures and modify oceanic circulation patterns that regulate global climate through heat transport between equatorial and polar regions. These oceanic effects would persist long after atmospheric dust clears and solar radiation returns to normal levels. Seasonal disruption would occur as atmospheric dust eliminates normal seasonal temperature variations and creates artificially extended winter conditions that disrupt biological cycles dependent on seasonal temperature and photoperiod cues, affecting animal migration patterns, reproductive cycles, and hibernation schedules across species adapted to predictable seasonal environmental changes. Human survival challenges would intensify as agricultural failures create global food shortages, while heating systems struggle to maintain habitable temperatures under sustained cold conditions, creating refugee crises as populations abandon agricultural regions and migrate toward areas with better survival prospects. Energy consumption for heating would increase dramatically while renewable energy systems dependent on solar radiation experience reduced output. Atmospheric optical effects would create distinctive sky coloration patterns as suspended dust particles scatter sunlight preferentially according to wavelength-dependent scattering cross-sections, potentially creating orange or red sky appearances reminiscent of major volcanic eruptions, while simultaneously reducing overall sky brightness to levels resembling dawn or dusk conditions throughout normal daylight hours. Stratospheric ozone depletion could occur if impact-generated chemical species catalyze ozone destruction reactions, similar to those caused by volcanic aerosols, creating additional environmental stress through increased ultraviolet radiation exposure when atmospheric dust eventually clears and solar radiation returns to normal intensities. These ozone effects would persist longer than dust-induced cooling and create ongoing biological hazards. Psychological effects on human populations would prove significant, as prolonged darkness and cold conditions create seasonal affective disorder symptoms across global populations, while economic disruption from agricultural failures and energy shortages generates social stress and political instability that compounds direct environmental effects of atmospheric darkening. Ecosystem recovery timescales would vary dramatically between different biological communities, with some species adapting to reduced light conditions while others experience population crashes that require decades or centuries for recovery through immigration from refugia or evolutionary adaptation to modified environmental conditions. Forest ecosystems would prove particularly vulnerable to sustained low-light conditions. The implications of global atmospheric darkening extend beyond immediate climate effects to encompass long-term environmental modifications that could trigger evolutionary adaptations and ecological reorganizations comparable to natural climate transitions that have shaped biological evolution throughout Earth's history, demonstrating that single catastrophic events can create environmental pressures that influence biological development over geological timescales. The vaporization and dispersal of 3IATLAS's nucleus during impact would introduce approximately 7 billion tons of alien chemical compounds into Earth's environmental systems, creating contamination patterns that spread isotopically anomalous materials and exotic organic molecules throughout atmospheric, hydrological, and biological reservoirs across the planet. Mass spectrometric analysis of environmental samples collected after impact would reveal chemical signatures unlike anything found in Earth's natural geochemical cycles: deuterium-enriched water molecules, carbon compounds with alien isotope ratios, and heavy metal concentrations that reflect stellar nucleosynthesis processes operating around massive stars unknown to solar system chemistry. Atmospheric contamination would begin immediately as impact vaporization converts solid nucleus materials into gaseous species that mix with Earth's atmosphere and subsequently condense onto surfaces worldwide through precipitation processes that carry alien chemistry into terrestrial watersheds, soil systems, and biological food webs. These atmospheric transport mechanisms would distribute interstellar chemical signatures across global distances within months of impact, creating contamination patterns that reflect wind circulation and precipitation patterns rather than proximity to the impact site. Groundwater contamination scenarios reveal pathways through which alien materials could penetrate deeply into subsurface aquifer systems, as infiltrating precipitation carries dissolved interstellar compounds through soil layers and into underground water supplies that provide drinking water for human populations and agricultural irrigation systems. The persistence of these contaminants in groundwater would create long-term exposure scenarios where alien chemistry continues affecting human health and ecosystem function for decades or centuries after initial contamination events. Heavy metal toxicity emerges as a primary concern as impact vaporized materials include metallic elements with isotopic compositions that differ from terrestrial standards, potentially creating biological toxicity through mechanisms that remain poorly understood since terrestrial organisms have never encountered materials with such exotic chemical signatures. Laboratory studies of toxicity using analog materials suggest that even familiar elements could exhibit unusual biological effects when present with alien isotopic ratios and chemical associations. Organic compound contamination would introduce complex carbon-based molecules with structural characteristics and stereochemical properties that differ from terrestrial biochemistry, creating potential interactions with biological systems through molecular recognition pathways that evolved to respond to terrestrial organic chemistry, but might respond unpredictably to alien molecular architectures. These organic contaminants could theoretically interfere with enzymatic processes and metabolic pathways in ways that prove difficult to predict or counteract. Only took atmospheric and hydrological transport processes a few months to distribute alien contaminants throughout global environmental systems and create exposure pathways that would persist for decades as contaminated materials cycle through biogeochemical processes that concentrate and redistribute alien chemistry according to natural processes that were never designed to handle interstellar chemical signatures. Bioaccumulation mechanisms would concentrate alien contaminants in biological tissues as organisms absorb and metabolize foreign chemical compounds that become incorporated into cellular structures and biochemical pathways, potentially creating enhanced toxicity effects as contaminant concentrations increase through food, web transfer from primary producers to apex predators. These bioaccumulation patterns would vary between different species depending on metabolic pathways and dietary characteristics. Soil chemistry modifications would alter agricultural productivity as alien compounds change soil pH, nutrient availability, and microbial community structure in ways that could prove beneficial or detrimental to crop production, depending on specific chemical interactions between interstellar materials and terrestrial soil systems. Some alien compounds might function as novel fertilizers, while others could create toxic conditions that prevent plant growth and soil biological activity. The discovery that certain alien isotopes undergo radioactive decay with half-lives that span human timescales means that contaminated regions would experience ongoing radiation exposure as unstable isotopes gradually decay and release ionizing radiation that could create additional health hazards beyond chemical toxicity effects. These radiological contamination patterns would require monitoring and remediation strategies developed specifically for exotic isotope compositions. Marine ecosystem contamination would occur as atmospheric deposition and runoff transport alien materials into oceanic systems, where they become incorporated into marine food webs through uptake by phytoplankton and subsequent transfer through fish populations that serve as food sources for human consumption. The global distribution of marine contamination would affect seafood safety and oceanic biological productivity across entire ocean basins. Pharmaceutical interactions could create unexpected medical complications as alien chemical compounds interfere with drug metabolism and therapeutic effectiveness in ways that remain unpredictable based on limited understanding of how extraterrestrial chemistry might interact with human biochemistry and pharmaceutical compounds designed for terrestrial biological systems. These interactions could affect both prescription medications and over-the-counter treatments. Agricultural contamination would require development of new food safety protocols and crop screening procedures to detect alien chemical signatures in food supplies, while simultaneously developing remediation strategies for contaminated agricultural soils that might require decades of treatment before returning to safe production levels. The global nature of contamination would affect international food trade and agricultural economics across all food-producing regions. Drinking water treatment challenges would emerge as conventional water purification systems prove inadequate for removing alien chemical compounds that exhibit unknown physical and chemical properties, requiring development of specialized treatment technologies capable of detecting and removing interstellar contaminants from municipal water supplies. These treatment requirements would create enormous infrastructure costs and technical challenges for water utility systems worldwide. Environmental monitoring programs would require enhancement to detect and quantify alien chemical signatures in environmental samples using analytical techniques capable of distinguishing interstellar compounds from natural terrestrial chemistry, creating needs for new analytical methods and instrumentation specifically designed for identifying extraterrestrial contamination in complex environmental matrices. Remediation strategies for contaminated sites would face unprecedented challenges as conventional environmental cleanup techniques prove inadequate for addressing contamination involving chemical compounds with unknown environmental behavior and toxicity characteristics, requiring development of new remediation technologies and approaches specifically designed for handling alien chemical contamination scenarios. Long-term environmental fate modeling would require new theoretical frameworks for predicting how alien chemical compounds behave in terrestrial environmental systems over timescales spanning decades to centuries. As existing environmental fate models were developed using terrestrial chemical databases that lack information about interstellar compound behavior under Earth environmental conditions, the implications of global chemical contamination extend beyond immediate toxicity concerns to encompass fundamental alterations to Earth's geochemical cycles and environmental chemistry that could influence biological evolution and ecological development for millions of years as alien chemical signatures become permanently incorporated into Earth's environmental systems and biological communities. The unprecedented introduction of interstellar organic compounds and potentially viable microorganisms into Earth's biosphere would create the first confirmed case of extraterrestrial biological exposure in planetary history, subjecting terrestrial life forms to chemical and potentially biological agents that evolved under stellar conditions radically different from those that shaped Earth's biochemistry. Laboratory analysis of impact debris would reveal amino acids with mirror image chirality compared to terrestrial proteins. nucleotide analogues with alternative base pairing capabilities, and complex organic polymers whose molecular architectures differ systematically from any compounds produced by Earth's biological evolution. Microbial exposure scenarios present the most immediate biological risks, as hypothetical extremophile organisms embedded within 3IATLAS's protective matrices could theoretically survive impact heating and introduce alien microbiological agents into terrestrial ecosystems, where they might interact with indigenous bacteria and archaea through horizontal gene transfer mechanisms that could alter the genetic composition of Earth's microbial communities. These microscopic encounters would operate below the threshold of direct observation, yet could trigger biological changes that propagate throughout global ecosystems. Immune system responses to alien biochemistry would prove unpredictable, as terrestrial organisms encounter molecular patterns that differ systematically from evolutionary experience, potentially triggering autoimmune reactions or immunological suppression, as biological defense systems struggle to categorize and respond to chemical signals that operate outside normal biological recognition pathways. Laboratory studies using synthetic alien compounds suggest that immune responses could range from hyperactivity to complete failure depending on molecular structural similarities to terrestrial biochemistry. Enzymatic interactions between alien organic compounds and terrestrial biochemical pathways could create metabolic disruptions as foreign molecules compete with natural substrates for enzyme binding sites or act as irreversible inhibitors that block essential biochemical processes. Computer modeling of enzyme-substrate interactions reveals that even minor structural differences between alien and terrestrial compounds could create dramatic differences in biochemical activity and metabolic efficiency. Plant biology exposure effect would manifest as agricultural crops and natural vegetation encounter alien organic compounds through root uptake and atmospheric absorption, potentially creating growth abnormalities, reproductive failures, or enhanced biological activity depending on whether alien compounds prove toxic, neutral, or beneficial to plant metabolic systems. Greenhouse studies using analog compounds indicate that plant responses could vary dramatically between different species and soil conditions. Only took biological transport mechanisms a few weeks to distribute alien organic compounds throughout food webs, as atmospheric deposition and groundwater infiltration create exposure pathways that affect organisms across multiple trophic levels simultaneously, creating complex ecological interactions where alien chemistry influences biological communities through both direct toxicity effects and indirect effects on species interactions and ecosystem function. Genetic incorporation possibilities arise if alien nucleotide analogues prove sufficiently similar to terrestrial DNA and RNA components to undergo incorporation into genetic systems through natural DNA repair and replication processes, potentially creating hybrid genetic systems that combine terrestrial and extraterrestrial genetic information in ways that could influence evolutionary trajectories for affected organisms. These genetic modifications could prove either beneficial or detrimental depending on functional compatibility between alien and terrestrial genetic systems. Protein folding disruptions could occur as alien amino acids become incorporated into protein synthesis pathways and create structural modifications that alter protein stability, enzyme activity, and cellular function through mechanisms that remain largely unpredictable based on limited understanding of how alternative amino acid compositions affect protein architecture and biological activity under physiological conditions. The mystery of biological chirality interactions emerges as alien organic compounds with opposite molecular handedness could theoretically interact with terrestrial biochemistry through mechanisms that reverse normal enzyme specificity and create biochemical processes that operate according to mirror image stereochemistry, potentially generating toxic metabolic byproducts or creating entirely novel biochemical pathways that complement existing terrestrial metabolism. Symbiotic relationship modifications could develop as alien organic compounds alter the chemical communication systems that regulate mutualistic interactions between different species, potentially disrupting nitrogen fixation in legume root nodules, mycorrhizal associations in forest ecosystems, or intestinal microbiome function in animal digestive systems. These symbiotic disruptions could create cascading ecological effects that exceed direct toxicity impacts. Evolutionary adaptation pressures would intensify as biological communities experience novel selection pressures from alien chemical exposure, potentially accelerating evolutionary adaptation toward tolerance or utilization of extraterrestrial compounds, while simultaneously creating extinction pressures for species unable to adapt to modified chemical environments. These evolutionary responses could operate over timescales ranging from bacterial generations to decades for larger organisms. Cancer risk assessments would require development of new frameworks for evaluating carcinogenic potential of chemical compounds with no terrestrial analogues and unknown mechanisms of biological interaction, creating challenges for public health agencies attempting to establish exposure limits and safety protocols for managing alien chemical contamination in human populations. Reproductive biology effects could manifest as alien compounds interfere with hormonal signaling systems and developmental processes that control reproduction in terrestrial organisms, potentially affecting fertility rates, embryonic development, and reproductive success across species ranging from soil microorganisms to large vertebrates including humans. These reproductive effects could have long-term demographic consequences for affected populations. Pharmaceutical development opportunities could emerge as alien organic compounds provide novel molecular scaffolds for drug development and therapeutic applications, potentially leading to breakthrough medical treatments that exploit unique biochemical properties unavailable through terrestrial natural product chemistry. The pharmaceutical industry would face both opportunities and challenges in developing and testing drugs derived from extraterrestrial sources. Biosafety protocols would require fundamental revision to address exposure scenarios involving biological agents with unknown properties and unpredictable interactions with terrestrial life forms, creating needs for new containment procedures, monitoring systems, and emergency response protocols specifically designed for managing extraterrestrial biological contamination events. Agricultural biotechnology applications could theoretically benefit from alien genetic material that provides novel traits for crop improvement, including enhanced stress tolerance, modified nutritional profiles, or improved yield characteristics that could prove valuable for addressing global food security challenges, while simultaneously creating regulatory challenges for managing genetically modified organisms containing extraterrestrial genetic components. The implications of biological exposure to interstellar organic compounds extend beyond immediate toxicity and adaptation effects to encompass fundamental questions about the compatibility and integration of biochemical systems that evolved under different stellar conditions, potentially providing insights into universal aspects of biochemistry, while revealing the extent to which life's molecular foundations remain dependent on specific environmental and chemical conditions. The enormous mass and velocity of 3IATLAS's impact would create sufficient momentum transfer to Earth's rotational and orbital systems to produce measurable alterations in planetary dynamics, including temporary modifications to the length of Earth's day, subtle changes in rotational axis orientation, and minor perturbations to orbital characteristics that could influence climate patterns and astronomical phenomena for centuries after impact. Computer simulations indicate that the impact could alter Earth's rotation rate by microseconds per day, while imparting angular momentum changes that modify the planet's rotational energy and create complex interactions between rotational dynamics and tidal effects from the Moon and Sun. Angular momentum conservation principles require that impact momentum becomes incorporated into Earth's rotational motion through mechanisms that depend critically on impact location, angle, and velocity, with equatorial impacts producing different rotational effects than polar impacts and retrograde impacts, creating opposite rotational modifications compared to prograde collisions. The specific geometry of 3IATLAS's hypothetical impact trajectory would determine whether Earth's rotation accelerates or decelerates, and whether rotational axis orientation shifts toward or away from current polar alignment. Rotational axis perturbations would create modifications to Earth's obliquity, the angle between rotational axis and orbital plane, that could alter seasonal intensity patterns and climate stability through changes in how solar radiation distributes across latitudinal zones throughout annual orbital cycles. Even small obliquity changes measuring fractions of degrees could modify ice cap stability, atmospheric circulation patterns, and seasonal temperature variations in ways that influence global climate evolution over geological timescales. Tidal interaction modifications would emerge as altered rotational characteristics change the gravitational coupling between Earth and Moon, potentially affecting lunar orbital evolution and tidal force patterns that influence oceanic circulation, coastal erosion rates, and biological processes dependent on tidal cycling. These gravitational modifications would operate through complex celestial mechanics that couple rotational and orbital dynamics across the Earth-Moon system. The discovery that major impacts can create temporary global seismic oscillations means that 3IATLAS could trigger free oscillation modes where Earth rings like a bell for hours or days after impact, creating global vibration patterns that could be detected by seismographic networks worldwide and provide unprecedented data about Earth's internal structure and mechanical properties under extreme excitation conditions. Only took impact momentum transfer a few seconds to alter planetary rotational dynamics and initiate modifications to Earth's astronomical characteristics that would persist for centuries or millennia as gravitational interactions with the Moon and Sun gradually restore original rotational configurations through tidal dissipation processes that operate over geological timescales. Precession rate modifications could alter the timing of astronomical cycles that influence long-term climate patterns, including the precession of equinoxes that affect seasonal timing relative to orbital position, and creates variations in solar radiation intensity that contribute to ice age cycles and long-term climate evolution. These astronomical modifications could influence climate stability for thousands of years after impact through alterations to Milankovitch cycle timing. Gravitational field perturbations would create temporary modifications to Earth's gravity field as impact-generated structural changes alter mass distribution within Earth's crust and mantle, potentially affecting satellite orbits, GPS precision, and gravitational measurements used for geological surveys and resource exploration. These gravitational anomalies would provide lasting signatures of impact effects that persist long after surface features heal through geological processes. The mystery of core-mantle coupling effects arises as seismic waves from major impacts could theoretically alter the dynamic interactions between Earth's solid mantle and liquid outer core that control magnetic field generation and rotational dynamics, potentially creating temporary modifications to geomagnetic field strength and orientation that affect navigation systems and radiation protection mechanisms. Orbital eccentricity changes could occur if impact momentum transfer affects Earth's orbital velocity sufficiently to modify orbital shape and distance variations from the Sun, creating alterations to seasonal intensity patterns and annual climate cycles that could influence atmospheric circulation and oceanic temperature distributions. These orbital modifications would prove extremely small, yet potentially detectable through precise astronomical measurements. Chandler wobble perturbations would affect the natural oscillation of Earth's rotational axis that creates small variations in polar position over periods of approximately 14 months, potentially creating enhanced polar motion that could affect precision navigation systems and astronomical observations requiring exact knowledge of Earth's rotational orientation relative to celestial reference frames. Gravitational wave generation from the impact event could theoretically create detectable signals for gravitational wave observatories, as the sudden mass acceleration during impact generates ripples in spacetime that propagate outward at light speed, providing exotic astronomical observations of gravitational effects created by planetary-scale impact processes that operate under conditions approaching those found in neutron star collisions. Magnetic field interactions could modify Earth's magnetosphere configuration as impact-generated plasma and electrical currents interact with the planetary magnetic field and create temporary modifications to radiation belt structure and magnetic field geometry that affect satellite operations. Cosmic ray shielding and auroral activity patterns across polar regions. Atmospheric angular momentum transfer would couple impact-modified rotational dynamics to atmospheric circulation patterns, as conservation of angular momentum requires that changes in solid Earth rotation create compensating modifications to atmospheric motion, potentially affecting jet stream patterns, storm track configurations, and global weather system organization. Tidal energy dissipation rates would change as modified rotational characteristics alter the efficiency of tidal friction processes that gradually slow Earth's rotation and cause lunar orbital recession, potentially affecting the long-term evolution of the Earth-Moon system and tidal force patterns that influence oceanic mixing, biological cycles, and coastal geomorphology. Satellite orbital perturbations would affect artificial satellites and space debris as modifications to Earth's gravitational field and rotational characteristics create orbital prediction errors and require trajectory corrections for maintaining satellite constellation configurations used for communication, navigation, and Earth observation systems that depend on precise orbital mechanics. The implications of planetary dynamic modifications extend beyond immediate mechanical effects to encompass long-term alterations to Earth's astronomical characteristics that could influence climate stability, biological evolution, and geological processes for millions of years as modified rotational and orbital dynamics interact with solar system gravitational environments to create complex evolutionary pathways for planetary system development. The enormous electrical energy generated by 3IATLAS's hypervelocity impact would create electromagnetic pulse effects comparable to the most powerful solar flares or high-altitude nuclear detonations, sending waves of electromagnetic radiation across the radio frequency spectrum that could disable or destroy electronic systems across continental regions and create global disruptions to technological infrastructure dependent on sensitive electronic components. The impact-generated plasma would accelerate charged particles to high velocities and create rapidly changing magnetic fields that induce powerful electrical currents in conducting materials ranging from power transmission lines to computer microprocessors. Radio frequency emissions from the impact event would propagate at light speed across the electromagnetic spectrum, creating signal interference and communication blackouts that affect everything from cellular telephone networks to GPS navigation systems and internet infrastructure that relies on satellite communications and terrestrial wireless networks. The electromagnetic signature would be detectable by radio astronomy facilities worldwide and create distinctive signals that could theoretically alert extraterrestrial observers to major geological events occurring on Earth. Power grid vulnerabilities would prove especially severe as electromagnetic pulse effects induce surge currents in electrical transmission networks that exceed design tolerances and create cascading failures across interconnected power systems, potentially leaving entire continental regions without electrical power for extended periods, while utility companies replace damaged transformers and transmission equipment. The economic costs of power grid restoration could exceed the direct physical damage from impact effects. Electronic device destruction would affect consumer electronics, industrial control systems, and medical equipment as electromagnetic pulse energy couples into electronic circuits and creates voltage spikes that exceed component ratings and cause permanent damage to semiconductor devices, integrated circuits, and sensitive electronic components. The replacement of destroyed electronic infrastructure would create enormous logistical challenges and economic costs. Satellite constellation disruptions would occur as electromagnetic pulse effects and impact-generated debris clouds affect orbital assets used for communication, navigation, weather monitoring, and Earth observation systems that provide essential services for global commerce, transportation, and emergency response operations. The loss of satellite capabilities would create additional communication challenges during post-impact recovery efforts. Only took electromagnetic energy a few microseconds to propagate from the impact site and begin affecting electronic systems across global distances, creating nearly instantaneous technological disruptions that could persist for months or years, as damaged infrastructure requires replacement and restoration through supply chains that might themselves be affected by electromagnetic pulse damage. Induced current generation in metallic infrastructure would create electrical surges in pipelines, railroad tracks, and metallic building structures that could cause corrosion acceleration, structural damage, and fire hazards as electromagnetic induction creates unwanted electrical currents that exceed design specifications for electrical isolation and surge protection systems. Atmospheric ionization effect would create electromagnetic propagation anomalies that affect radio communication, radar systems, and wireless networks as ionized atmospheric regions modify electromagnetic wave propagation characteristics and create signal reflection, absorption, and scattering effects that disrupt normal communication system operation for hours or days after impact. The mystery of electromagnetic pulse coupling efficiency reveals that impact-generated electromagnetic fields could induce destructive currents in electronic systems located thousands of kilometers from the impact site, with coupling efficiency depending on antenna geometry, shielding effectiveness, and electronic component vulnerability to electromagnetic interference effects that remain difficult to predict without detailed electromagnetic modeling. Magnetic field perturbations would affect compass navigation systems and magnetic survey instruments, as impact-generated electromagnetic effects create temporary modifications to local magnetic field configurations that could persist for days or weeks after impact, while electromagnetic induction effects gradually dissipate through resistive losses in conducting materials. Fiber optic network resilience would provide communication advantages compared to copper-based networks, as optical fibers prove largely immune to electromagnetic pulse effects. Yet fiber optic systems remain vulnerable to power supply disruptions and electronic component damage in terminal equipment, that converts optical signals to electrical signals for processing and routing. Aviation system failures would create flight safety hazards as electromagnetic pulse effects disable aircraft navigation, communication, and flight control systems during critical flight phases, potentially creating aviation emergencies across continental regions as aircraft lose GPS navigation, radio communication, and electronic flight control capabilities simultaneously. Financial system disruptions would affect electronic banking, credit card processing, and financial trading systems as electromagnetic pulse damage to computer networks and communication systems creates temporary or permanent loss of financial transaction capabilities, potentially triggering economic disruptions that exceed direct physical damage from impact effects. Medical equipment vulnerabilities would create healthcare emergencies as electromagnetic pulse effects disable life support systems, diagnostic equipment, and computerized medical devices that provide essential patient care functions, creating immediate threats to critically ill patients while simultaneously overwhelming emergency medical systems that might themselves be affected by electromagnetic disruptions. Industrial control system failures would affect manufacturing facilities, chemical processing plants, and utility operations as electromagnetic pulse effects disable computerized control systems that regulate industrial processes, potentially creating secondary hazards from uncontrolled chemical reactions, equipment failures, and safety system malfunctions. Emergency response coordination challenges would multiply as electromagnetic pulse effects disable communication systems, transportation infrastructure, and emergency services equipment needed for disaster response operations, creating scenarios where emergency responders cannot communicate effectively or coordinate rescue operations during the critical initial response period following impact. Electromagnetic shielding effectiveness would vary dramatically between different types of electronic equipment and facilities, with military systems generally providing better electromagnetic pulse protection compared to civilian infrastructure. Yet even hardened systems could experience degraded performance or component failures under extreme electromagnetic pulse conditions generated by major impact events. Recovery timeline estimation for electromagnetic pulse damage reveals that restoration of full technological capability could require months to years, depending on the extent of component damage and the availability of replacement equipment, creating extended periods of reduced technological capability that could affect economic productivity, emergency response effectiveness, and quality of life measures across affected populations. The implications of electromagnetic pulse effects extend beyond immediate technological disruption to encompass fundamental vulnerabilities in modern technological civilizations' dependence on electronic systems and electromagnetic communication networks that could prove inadequate for maintaining societal function during extreme electromagnetic disturbance events generated by cosmic impact phenomena. The massive injection of atmospheric dust and chemical aerosols from 3IATLAS's impact would trigger fundamental alterations to Earth's climate system that persist for decades beyond the initial atmospheric darkening period, creating long-term modifications to temperature patterns, precipitation distributions, and atmospheric circulation that could reshape global weather systems and trigger cascading environmental changes affecting agriculture, water resources, and ecosystem stability worldwide. Computer climate models predict that even after atmospheric dust settles and solar radiation returns to normal levels, the disruption to oceanic circulation patterns and atmospheric chemistry would create persistent climate anomalies that influence regional weather patterns for generations. Oceanic thermal inertia effects would create delayed climate responses as the enormous heat capacity of Earth's oceans buffers and redistributes temperature changes over timescales spanning decades, with initial atmospheric cooling gradually penetrating into deeper oceanic layers and modifying global heat transport mechanisms that regulate climate stability. The gradual oceanic temperature adjustment would create climate recovery patterns that unfold over periods measuring decades rather than the months required for atmospheric dust removal. Atmospheric chemistry modifications would persist long after dust particle removal, as impact vaporized materials alter atmospheric composition through chemical reactions that create new aerosol populations and modify atmospheric chemistry cycles governing ozone formation, acid precipitation, and greenhouse gas concentrations. These atmospheric chemistry changes could create lasting modifications to radiative balance and atmospheric optical properties that influence climate even after visible atmospheric effects disappear. Ocean current disruptions would emerge as impact-induced temperature changes alter density gradients that drive thermohaline circulation patterns responsible for global heat transport between equatorial and polar regions, potentially triggering modifications to Gulf Stream intensity, Antarctic circumpolar current strength, and deep water formation rates that could persist for centuries as oceanic circulation systems slowly readjust to modified thermal conditions. Monsoon system modifications could affect seasonal precipitation patterns across tropical and subtropical regions, as altered atmospheric temperature gradients change land-ocean thermal contrasts that drive monsoon circulation, potentially creating long-term alterations to agricultural productivity and water resource availability across regions dependent on monsoon precipitation for food production and freshwater supplies. Only took atmospheric circulation a few months to establish new climate patterns that would persist for decades as feedback mechanisms between oceanic thermal adjustment, atmospheric chemistry modifications, and circulation pattern changes create complex climate system responses that unfold over timescales far exceeding the initial atmospheric disturbance period. Ice sheet stability changes could occur as modified temperature and precipitation patterns affect polar ice accumulation and melting rates, potentially triggering ice sheet growth or retreat that would influence global sea level and coastal geography for thousands of years, as ice sheet dynamics respond slowly to climate modifications through mechanisms that operate over geological timescales. Agricultural zone shifts would require fundamental reorganization of global food production systems as modified temperature and precipitation patterns alter crop viability across different latitude bands, potentially rendering traditional agricultural regions unsuitable for current crops while opening new agricultural opportunities in previously marginal regions. These agricultural transitions would require massive infrastructure investments and crop variety development. The mystery of climate system sensitivity to impact perturbations reveals that even temporary atmospheric disturbances could trigger long-term climate state changes if impact effects push climate systems beyond critical thresholds that initiate irreversible transitions between different climate regimes, similar to natural climate transitions that have occurred throughout Earth's geological history. Vegetation pattern modifications would reshape global ecosystem distributions as altered temperature and precipitation regimes favor different plant communities and create shifts in forest grassland boundaries, desert margins, and Arctic treeline positions that influence carbon storage, biodiversity patterns, and ecosystem service provision across continental regions. Atmospheric circulation reorganization could create persistent changes to jet stream patterns, storm track configurations, and pressure system distributions that alter regional weather patterns and extreme event frequencies, potentially increasing drought, flood, and storm risks in some regions while reducing meteorological hazards in others. Carbon cycle perturbations would affect global atmospheric carbon dioxide concentrations, as impact-induced ecosystem disruptions alter vegetation carbon storage and soil organic matter decomposition rates, potentially creating feedback effects that amplify or moderate climate changes through modifications to natural carbon sequestration and release processes. Hydrological cycle modifications would alter global water resource distribution as changed precipitation patterns affect river flow regimes, groundwater recharge rates, and lake level dynamics, creating long-term water resource challenges that require infrastructure adaptation and water management strategy revision across affected regions. Extreme weather frequency changes could alter the statistical characteristics of meteorological hazards as modified atmospheric circulation patterns change the probability distributions for heat waves, cold snaps, droughts, floods, and severe storms, creating new risk assessment challenges for emergency planning and infrastructure design applications. Seasonal pattern disruptions would affect biological processes dependent on predictable seasonal cycles, as altered temperature and precipitation timing affects plant flowering, animal migration, and reproductive cycles that evolve to synchronize with historical seasonal patterns, potentially creating ecological mismatches that affect ecosystem function and biodiversity. Climate variability modifications could alter the natural oscillation patterns like El Niño and Atlantic multi-decadal oscillation that regulate interannual climate variability and affect regional weather patterns, potentially creating new climate variability modes or modifying existing oscillation frequencies and amplitudes that influence long-term weather prediction capabilities. Adaptation requirement assessments reveal that human societies would face fundamental challenges in adapting infrastructure, agricultural systems, and water resource management to accommodate persistent climate modifications that exceed the range of historical climate variability, requiring unprecedented coordination of adaptation strategies across global scales. The implications of long-term climate system perturbations extend beyond meteorological changes to encompass fundamental alterations to Earth's environmental conditions that could influence human civilization development, ecological evolution, and planetary habitability for thousands of years as climate system recovery processes operate through complex feedback mechanisms that remain partially understood from current climate science perspectives. The geological record would preserve 3IATLAS's impact as a distinctive stratigraphic boundary layer that future geologists could recognize millions of years later through characteristic signatures that include shocked minerals, iridium anomalies from vaporized nucleus materials, and distinctive sedimentary features that mark one of the most significant geological events in Earth's history. This impact horizon would appear in sedimentary sequences worldwide as a thin clay layer enriched with platinum group elements, shocked quartz grains, and spherical glass beads formed from impact-generated melt droplets that cooled during ballistic transport across continents. Shocked mineral assemblages within the impact layer would provide definitive evidence of extreme pressure and temperature conditions that occur only during major impact events, including high-pressure polymorphs of common minerals like diamond formed from graphite, stishovite created from quartz, and other exotic mineral phases that require pressures exceeding those found anywhere else in Earth's geological environments. These shocked mineral signatures would persist indefinitely in the geological record and provide unmistakable evidence of catastrophic impact processes. Isotopic signatures preserved in impact layer sediments would reveal the alien chemical composition of 3IATLAS's nucleus through distinctive isotope ratios that differ systematically from terrestrial materials, including enhanced osmium-187 concentrations, anomalous platinum group element patterns, and exotic isotope ratios of common elements that reflect stellar nucleosynthesis processes operating around massive stars unknown to solar system materials. Paleomagnetic records within impact-related deposits would preserve evidence of electromagnetic effects generated during impact, as rapidly changing magnetic fields create distinctive magnetic orientations in iron-bearing minerals that record the intense electromagnetic environment present during crater formation. The paleomagnetic signatures would provide information about impact-generated magnetic field effects and electromagnetic pulse phenomena. Biostratigraphic boundaries would mark the impact horizon through fossil assemblages that record biological extinctions and evolutionary changes triggered by impact-induced environmental disruptions, creating distinctive paleontological signatures where pre-impact fossil assemblages give way to post-impact biological communities that reflect adaptation to modified environmental conditions and ecosystem reorganization. Only took geological processes a few thousand years to bury impact-related deposits under subsequent sedimentary layers that preserve detailed records of environmental recovery following catastrophic impact effects, creating stratigraphic sequences that chronicle both immediate impact consequences and long-term environmental adaptation to modified planetary conditions. Spheral bed formation would create distinctive sedimentary layers composed of glass spheres formed from impact melt droplets that cooled during atmospheric transport, with spheral size distributions and chemical compositions that preserve information about impact energy, atmospheric transport distances, and cooling processes that operated during ejector emplacement across global distances. Tsunami deposit preservation in coastal sedimentary sequences would record evidence of impact-generated water displacement through distinctive sedimentary structures that include marine fossils transported inland, graded bedding sequences that record multiple wave arrivals, and erosional unconformities that mark sea level changes associated with catastrophic water displacement events. The mystery of geochemical anomaly preservation reveals that certain impact-related chemical signatures persist through millions of years of weathering, erosion, and metamorphic processes, while others become modified or destroyed, creating selective preservation patterns that influence which aspects of impact events remain detectable in ancient geological records and affect interpretation of impact frequency and magnitude through Earth's history. Carbon isotope excursions within impact boundary sediments would preserve evidence of biological productivity disruptions and atmospheric chemistry modifications through distinctive carbon isotope patterns that reflect changes in photosynthetic activity, organic matter preservation, and atmospheric carbon dioxide concentrations that occurred during post-impact environmental recovery periods. Crater structure preservation potential depends on subsequent geological processes, including erosion rates, tectonic activity, and sedimentary burial that determine whether impact crater morphology remains recognizable over geological timescales, with preservation probability varying between different geological settings and climatic conditions that affect erosion and sedimentation rates. Microtectite distributions would create widespread evidence of impact processes through microscopic glass fragments distributed across continental and oceanic sedimentary sequences, with microtectite abundance patterns and chemical compositions that preserve information about impact location, energy, and atmospheric transport processes that operated during global ejector distribution. Organic geochemistry preservation within impact boundary layers could theoretically preserve evidence of alien organic compounds introduced by nucleus vaporization, including distinctive biomarker molecules, unusual isotopic compositions in organic matter, and exotic molecular structures that remain detectable through advanced analytical techniques applied to ancient sedimentary organic matter. Sedimentary sequence disruption would create distinctive stratigraphic patterns where normal depositional processes were interrupted by impact-related sedimentation, including mass-wasting deposits, altered sedimentation rates, and unconformity development that records environmental disruptions and subsequent recovery processes that operated over timescales ranging from years to millennia. Trace fossil evidence would preserve behavioral responses of surviving organisms to post-impact environmental conditions through burrow patterns, feeding traces, and other biological structures that record how biological communities adapted to modified environmental conditions and ecosystem reorganization following catastrophic environmental disruption. Comparative stratigraphy across different geographical regions would reveal the global extent and regional variations of impact effects through correlation of impact boundary layers that preserve different aspects of impact processes depending on distance from impact site, local geological conditions, and environmental settings that influenced impact effect preservation. Geochronological dating of impact-related deposits would establish precise timing of impact events and environmental recovery processes through radiometric dating techniques applied to impact-generated minerals and post-impact sedimentary sequences, providing temporal frameworks for understanding the duration and pace of environmental recovery following major impact events. The implications of geological record preservation extend beyond scientific curiosity to encompass fundamental understanding of how catastrophic events influence planetary evolution and biological development over geological timescales, providing insights into natural hazard frequencies and environmental resilience that inform current understanding of planetary habitability and ecosystem stability under extreme perturbation conditions. Future geological surveys would recognize 3IATLAS impact signatures as boundary markers that correlate sedimentary sequences across global distances and provide temporal reference horizons for understanding Earth's geological and biological evolution, demonstrating how single catastrophic events create permanent geological records that influence scientific understanding of planetary history for millions of years after their occurrence. The recognition that 3IATLAS posed an existential threat to Earth would trigger unprecedented international coordination of planetary defense resources as space agencies, military organizations, and scientific institutions worldwide mobilize deflection technologies and intervention strategies designed to alter the comet's trajectory before impact becomes inevitable. Current planetary defense capabilities, developed primarily for conventional asteroid and comet threats originating within the solar system, would face extreme challenges when applied to an interstellar object approaching at velocities that provide minimal reaction time and whose exotic composition creates uncertainties in deflection effectiveness. Nuclear deflection strategies would represent the most powerful intervention option available, involving deployment of nuclear weapons designed to either destroy the incoming object through explosive fragmentation or alter its trajectory through momentum transfer from nuclear explosion shockwaves. Computer simulations reveal that nuclear deflection of interstellar objects requires careful consideration of detonation timing, explosive yield, and standoff distance to achieve optimal momentum transfer, while avoiding fragmentation that could create multiple impact threats distributed across wider geographical areas. Kinetic impactor missions would attempt to alter 3I-Atlas's trajectory through high-velocity spacecraft collisions that transfer momentum through purely mechanical mechanisms, yet the enormous mass and velocity of interstellar objects means that kinetic deflection requires impactor masses and velocities that exceed current spacecraft capabilities by substantial margins. Multiple coordinated kinetic impacts might achieve cumulative deflection effects sufficient to alter impact probability if executed with precise timing and trajectory planning. Gravitational tractor concepts involve positioning massive spacecraft near the approaching object to create gravitational forces that gradually modify its trajectory over extended time periods. Yet the extremely high approach velocity of interstellar objects provides insufficient time for gravitational tractor operations to achieve meaningful deflection before impact becomes unavoidable. These techniques remain viable only for objects detected years or decades before potential impact. Solar radiation pressure enhancement through deployment of reflective materials or solar concentrators could theoretically amplify natural radiation pressure effects and create continuous thrust forces that accumulate over time to produce trajectory modifications. Yet implementing such systems on rapidly approaching interstellar objects would require spacecraft rendezvous capabilities and deployment timescales that exceed current technological capabilities. Only took orbital mechanics calculations a few hours to reveal that deflection mission success probabilities decrease rapidly as detection to impact time diminishes, highlighting critical importance of early detection systems capable of identifying potentially hazardous interstellar objects years or decades before Earth encounter, rather than months or weeks that might be available with current astronomical survey capabilities. Ion beam deflection strategies would involve deploying spacecraft equipped with powerful ion propulsion systems to create continuous thrust forces acting on the target object over extended periods, gradually modifying trajectory through persistent low-thrust acceleration that accumulates over time to produce significant deflection. These techniques require long-duration spacecraft operations and substantial power generation capabilities that challenge current space technology. Laser ablation deflection would use high-power laser systems to vaporize surface materials and create rocket-like thrust through controlled mass ejection, potentially providing precise thrust vector control and continuous deflection capability that could operate over extended distances using ground-based or space-based laser installations. The effectiveness depends critically on surface composition and absorption characteristics that remain uncertain for exotic interstellar materials. The mystery of deflection effectiveness scaling reveals that interstellar objects might respond differently to deflection forces compared to solar system objects due to structural differences, composition variations, and mechanical properties that reflect formation under alternative stellar conditions, potentially requiring modification of deflection strategies and force calculations developed from experience with conventional asteroid and comet deflection scenarios. Fragmentation concerns arise when considering high-energy deflection methods that could break apart incoming objects into multiple fragments that create distributed impact threats across wider geographical regions, potentially transforming single large impact into multiple smaller impacts that collectively cause more widespread damage than unified impact events. Fragmentation avoidance requires careful selection of deflection methods and explosive yields. International coordination challenges would prove enormous, as planetary defense operations require unprecedented cooperation between nations with different technological capabilities, political systems, and strategic priorities while operating under extreme time pressure that prevents normal diplomatic negotiation processes. These coordination requirements would test international institutions and treaty frameworks under crisis conditions. Space infrastructure requirements for effective planetary defense exceed current launch capabilities and spacecraft manufacturing capacity by substantial margins, requiring development of heavy-lift launch systems, nuclear-capable spacecraft, and precision navigation technologies that could take decades to develop under normal circumstances, yet might be needed within months of threat detection. Mission failure contingency planning would require development of backup deflection strategies and alternative intervention approaches that could be implemented if primary deflection missions fail or prove insufficient to prevent impact, including evacuation planning, infrastructure protection, and emergency response preparation that could minimize casualties and economic damage from impact events. Cost-benefit analysis of planetary defense investments reveals that deflection mission costs measuring billions of dollars remain economically justified compared to potential impact damage that could exceed trillions of dollars in direct economic losses while causing environmental and social disruptions that persist for decades beyond initial impact events. Technology development priorities for enhanced planetary defense would focus on improved detection capabilities, rapid response spacecraft systems, nuclear deflection technologies, and international coordination mechanisms that could provide effective protection against interstellar impact threats while simultaneously advancing space exploration capabilities for scientific and commercial applications. Legal and ethical frameworks for planetary defense operations would require new international agreements governing the use of nuclear weapons in space, liability assignment for deflection mission failures, and decision-making authority for planetary defense operations that could affect all human populations regardless of national boundaries or political participation in deflection efforts. The implications of planetary defense against interstellar objects extend beyond immediate threat mitigation to encompass fundamental questions about humanity's technological capability to protect planetary habitability against cosmic hazards that operate on scales and timescales that challenge current technological and institutional capabilities while highlighting the interconnected nature of global survival in the face of natural disasters that transcend national boundaries. The Earth that emerges from 3IATLAS's hypothetical impact would represent a fundamentally transformed planet where geological, chemical, and biological systems operate according to modified principles that incorporate the lasting consequences of interstellar contamination and environmental disruption into new equilibrium states that differ systematically from pre-impact planetary conditions. Decades or centuries after impact, the global environment would exhibit chemical signatures, biological adaptations, and geological features that preserve evidence of this cosmic encounter while creating novel planetary characteristics that influence climate stability, biological evolution, and human civilization development for millions of years into the future. Atmospheric composition would retain subtle but permanent modifications, where trace quantities of alien isotopes and exotic compounds continue circulating through atmospheric chemistry cycles, creating distinctive spectroscopic signatures that would be detectable by future atmospheric monitoring systems and potentially recognizable to extraterrestrial observers capable of analyzing Earth's atmospheric composition through remote sensing techniques. These atmospheric modifications would represent humanity's first permanent planetary-scale technological signature, visible from interstellar distances. Biological evolution would proceed along modified pathways as terrestrial organisms adapt to environmental conditions that include trace contamination from interstellar organic compounds and altered atmospheric chemistry, potentially accelerating evolutionary adaptation while creating selection pressures that favor organisms capable of metabolizing or tolerating alien chemical signatures. Some species might develop enhanced capabilities for processing exotic compounds, while others experience extinction pressures that reshape global biodiversity patterns. Geological processes would incorporate alien materials into Earth's continuing geological evolution, as weathering, erosion, and sedimentation redistribute impact-delivered materials throughout sedimentary cycles that preserve interstellar chemical signatures in rock formations for billions of years. Future geological surveys would recognize these alien chemical markers as evidence of major cosmic events that contributed exotic materials to Earth's geological inventory. Human civilization would develop within a planetary context permanently altered by cosmic impact experience, potentially influencing cultural development, scientific priorities, and technological advancement directions as societies adapt to environmental conditions that include persistent reminders of cosmic vulnerability and planetary interconnectedness with broader galactic processes. The psychological and cultural impacts could prove as lasting as physical environmental changes. Only took cosmic encounter a few years to establish new environmental baselines that would persist for geological timescales, as Earth's environmental systems incorporate alien materials and impact-induced modifications into ongoing planetary evolution processes that operate over millions of years, while preserving chemical and biological evidence of this extraordinary cosmic event. Agricultural systems would adapt to modified soil chemistry and atmospheric conditions through development of crop varieties, tolerant to trace alien contamination, while potentially benefiting from novel chemical pathways that enhance plant nutrition or disease resistance. Agricultural biotechnology might exploit alien genetic materials or chemical compounds that provide advantages for food production under modified environmental conditions. Climate system reorganization would create new long-term climate patterns as oceanic circulation, atmospheric chemistry, and ice sheet dynamics reach new equilibrium states that incorporate the lasting effects of impact-induced perturbations. These climate modifications could influence habitability patterns and ecosystem distribution, while creating climate variability characteristics that differ from pre-impact patterns. The mystery of planetary resilience would be tested through Earth's response to the most severe environmental perturbation in human history, potentially revealing fundamental aspects of planetary system stability and recovery mechanisms that operate under extreme conditions while demonstrating the capacity of biological and geological systems to adapt to catastrophic environmental change. Technological development would be accelerated in directions related to planetary monitoring, environmental remediation, and cosmic hazard detection, as human societies develop enhanced capabilities for managing planetary-scale environmental challenges, while simultaneously advancing space exploration and planetary defense technologies stimulated by direct experience with cosmic impact consequences. Ecosystem reorganization would create new biological communities adapted to modified environmental conditions, while potentially exhibiting enhanced resilience to environmental perturbation through evolutionary selection for adaptability and stress tolerance. These modified ecosystems might develop novel ecological relationships and biological processes that exploit environmental characteristics created by cosmic contamination. Scientific advancement would benefit enormously from direct access to interstellar materials and impact-generated extreme conditions that provide natural laboratories for studying processes that normally require expensive experimental facilities or remain inaccessible to terrestrial investigation. The scientific insights gained could advance understanding of cosmic chemistry, extreme materials science, and planetary evolution processes. Economic adaptation would reshape global resource utilization patterns as societies develop new technologies for exploiting impact-delivered materials while adapting infrastructure and production systems to accommodate modified environmental conditions. Economic development could potentially benefit from novel resource opportunities while facing challenges from environmental remediation costs. Cultural evolution would incorporate cosmic impact experience into human knowledge systems, religious frameworks, and philosophical perspectives as societies develop new understanding of Earth's place in cosmic processes and humanity's relationship to galactic-scale phenomena that operate over timescales far exceeding human civilization development. Educational transformation would occur as scientific curricula incorporate direct experience with cosmic materials and planetary-scale environmental change into educational programs that prepare future generations to understand and manage planetary systems that exhibit characteristics unknown to pre-impact Earth. These educational modifications could enhance scientific literacy and environmental awareness. International cooperation would be strengthened through shared experience of global environmental challenge that demonstrates the interconnected nature of planetary habitability and the necessity for cooperative approaches to managing planetary-scale environmental systems that transcend national boundaries and require coordinated global response capabilities. Medical advancement could benefit from research into biological responses to alien chemical exposure, while developing new therapeutic approaches for managing environmental health challenges that arise from cosmic contamination. These medical developments could enhance human health, while advancing understanding of biochemical adaptation mechanisms. The implications of planetary transformation extend beyond immediate adaptation challenges to encompass fundamental questions about planetary evolution, biological resilience, and civilization development under conditions that include permanent cosmic influences operating through chemical, biological, and geological processes that connect Earth's environmental systems to galactic-scale phenomena and interstellar material circulation patterns. As this transformed Earth continues its orbital journey around the Sun, it carries within its atmospheric, geological, and biological systems the permanent chemical memory of an ancient cosmic wanderer that briefly intersected human awareness before becoming forever incorporated into planetary evolution processes that will influence Earth's development for millions of years, while preserving evidence of cosmic connectivity that spans interstellar distances and geological timescales. The profound stillness that follows our journey through this cosmic catastrophe carries with it a deeper understanding of Earth's delicate place within the vast mechanisms of galactic evolution, where ancient wanderers from distant stellar neighborhoods could theoretically reshape planetary destiny through encounters that transform geological timescales into human-relevant disasters. In contemplating what might have been, we discover not terror, but a quiet reverence for the cosmic forces that operate with patient indifference across distances and timescales that dwarf human experience, yet occasionally intersect our small world in ways that could redefine the very nature of terrestrial existence. The mathematical precision of orbital mechanics that guided 3IATLAS safely past Earth, rather than into collision, speaks to the fundamental randomness that governs cosmic encounters, tiny variations in trajectory, timing, or gravitational perturbation that determine whether interstellar visitors bring scientific wonder or existential catastrophe. This razor-thin margin between discovery and disaster reminds us that human civilization exists within a cosmic lottery, where the same gravitational laws that maintain planetary stability occasionally deliver challenges that exceed all earthly experience and technological preparation. Our thought experiment reveals how quickly cosmic scales can collapse into human relevance when interstellar objects transition from distant curiosities to immediate threats. Compressing millions of years of cosmic wandering into months of approaching crisis that would test every aspect of human technological capability, international cooperation, and civilizational resilience. The scenarios we've explored illuminate both humanity's remarkable scientific understanding and the fundamental limitations that constrain technological response to cosmic-scale phenomena. Yet within these sobering calculations lies a strange comfort, the recognition that Earth has survived countless cosmic encounters throughout its 4-billion-year history, absorbing impacts, adapting to catastrophic environmental changes, and continuing its biological evolution through catastrophes that transformed atmospheric composition, climate systems, and the very nature of life itself. Our planet carries within its geological record the scars and signatures of ancient impacts that once threatened global extinction, yet ultimately contributed to the environmental complexity that enabled biological innovation and evolutionary diversity. The resilience demonstrated by terrestrial life forms through previous mass extinction events suggests that Earth's biological systems possess remarkable capacity for adaptation and recovery, even under environmental conditions that exceed all previous evolutionary experience. While individual species and ecosystems might face catastrophic disruption, the fundamental processes of biological evolution continue operating through environmental transitions that create new ecological opportunities and evolutionary pathways previously unknown to planetary life. Only took 4 billion years of planetary evolution to create biological and geological systems capable of surviving cosmic catastrophes that would transform environmental conditions beyond anything found in recorded human experience, demonstrating that planetary habitability represents a robust phenomenon that persists through cosmic encounters that reshape atmospheric composition, climate patterns, and the chemical foundations of biological processes. The technological civilization that contemplates these cosmic scenarios represents Earth's first attempt to develop conscious planetary defense capabilities that could theoretically protect global environmental stability against cosmic threats through detection systems, deflection technologies, and international cooperation mechanisms that transcend the passive resilience strategies employed by previous biological communities facing cosmic hazards. This emerging technological capability places humanity in a unique position within Earth's evolutionary history, the first species capable of recognizing cosmic threats before they arrive, and potentially developing intervention strategies that could preserve existing environmental conditions rather than simply adapting to catastrophic environmental change after cosmic encounters transform planetary characteristics through impact processes. The profound interconnectedness revealed through our cosmic catastrophe scenarios highlights how local environmental conditions reflect galactic-scale processes that operate through stellar evolution, planetary formation, and interstellar material circulation patterns that occasionally deliver samples of cosmic chemistry to planetary surfaces through impact events that connect terrestrial biological evolution to cosmic nucleosynthesis and stellar formation processes. Each calculation of impact energy, atmospheric disruption, and biological consequence reminds us that Earth exists within cosmic environments that operate according to scales and rhythms that encompass yet transcend terrestrial experience, where stellar formation regions produce cosmic wanderers that carry within their ancient structures the chemical signatures of galactic evolution and stellar nucleosynthesis processes that operated long before Earth formed within the solar nebula. The scenarios we've contemplated transform 3IATLAS from scientific curiosity into philosophical teacher, demonstrating how cosmic mechanics operate with indifferent precision that occasionally creates intersection points where interstellar evolution meets planetary evolution through impact events that reshape environmental conditions and challenge biological adaptation across geological timescales that span the rise and fall of entire biological eras. In the growing silence of contemplation, we recognize that our cosmic visitor's safe passage represents one outcome within probability distributions that encompass both scientific discovery and civilizational challenge, where the same gravitational mathematics that delivered fascinating observations could theoretically deliver existential trials that test every aspect of planetary habitability and biological resilience. The peaceful departure of 3IATLAS toward its cosmic destiny carries with it humanity's growing awareness of cosmic vulnerability and planetary preciousness, knowledge that Earth's environmental stability depends on cosmic lottery systems that operate beyond human control, yet increasingly within human understanding and potentially within the reach of human technological intervention. As we drift toward rest, we carry the quiet recognition that cosmic wanderers like 3IATLAS represent both scientific opportunity and existential reminder, ancient messengers that connect Earth's biological evolution to galactic-scale processes while occasionally threatening to reshape planetary evolution through cosmic encounters that operate according to timescales and energy levels that dwarf terrestrial experience yet occasionally compress into human-relevant catastrophes. The eternal cosmic circulation continues wandering bodies carrying exotic chemistry and kinetic energy through gravitational pathways that occasionally intersect planetary evolution, testing biological resilience and challenging technological capability through encounters that demonstrate both cosmic beauty and cosmic power, operating through the same mathematical principles that govern stellar formation and planetary motion across the vast spaces and timescales of galactic evolution. Sleep well, cosmic wanderer. Sleep well, planetary resilience. Sleep well, human curiosity that contemplates both cosmic wonder and cosmic responsibility in equal measure.